So I'll be presenting B squared, N squared, N-way concurrent communication for our IoT devices. I just want to thank my colleagues who collaborated with my work, Zichen, Hongyu, Yao, Zhen, and my advisor, Dr. Zhu. Again, I'm from Maryland. So the problem that I'm going to present is dealing with devices with multiple radios. And this is a simplified example. So in this example, we have a device that has an IoT device that has a Bluetooth connection. And then you have a cell phone that has a Wi-Fi detection, communication. And in order for the Bluetooth device to talk to the Wi-Fi device, the current setup is the Bluetooth device sends a signal wirelessly to a gateway, right? And the gateway repeats that signal, transitioning from Bluetooth to Wi-Fi, and sends it to the Wi-Fi device. So it relies on this idea of this gateway. And the bad thing about this current system setup is that there's redundancy. There's two redundant messages being sent. You have a Bluetooth device, and the gateway has to forward this device. There is money for the hardware, which for every time you have one of these systems, you have to purchase this gateway, right? This gateway will become the bottleneck. It limits your network connection. It's essentially the router, and you have to purchase one of these routers. So as you can imagine, if you were to have thousands, hundreds of thousands of these devices, you have to have tons of these gateways, and it's inefficient. So what we want to do for our work, and to summarize it, is we want to remove the gateway. We want a Bluetooth device to be able directly to communicate with a Wi-Fi device. We want, while simultaneously for the Wi-Fi device to receive, of course, Wi-Fi signals. This decreases the need for that redundant message. It costs a lot less money. You don't need to buy these Bluetooth devices. And it's much easier. You can scale this with the exponential increase of IoT devices. So I'm not the first one that thought of this. So there's tons of work that's already been done on this area with cross-technology communications. I just want to highlight the few recent ones. So in eSense, they were able to get a cross-communication throughput by using what they consider alphabets. What they did was, in summary, short summary, is that they were able to change the packet sizes of your Wi-Fi devices. Your Bluetooth device, of course, can sample the length of that Wi-Fi device, and hence they were able to transmit alphabets. The other one is Freebie. I think someone from this paper is president of this conference. What they did is they actually changed they were able to use Bluetooth and Zigbee to measure the distances between beacons. And by measuring that distance, they were able to basically transmit bits. So basically they modulated the beacon rate. Thanks to them, of course, we want to continue this line of thought, is what happens if we modulate the power levels of the Bluetooth device? So by doing so, we're able to increase the number of devices that can simultaneously communicate to Wi-Fi, and we're able to use what we consider concurrent communications. We actually use data bits compared to beacons. So these are the current work. So I will make a couple of observations. So this is your standard Wi-Fi channel. It's a wideband channel. I think nowadays, it goes to 80 megahertz. So we just want to make an illustration. This is your standard Wi-Fi, which spans multiple frequencies, and you have the ability to transmit at different power. We also want to make the observation that BLE, Bluetooth Low Energy, uses the same band as Wi-Fi. Hence, what we hypothesize is that we can sense BLE using Wi-Fi's carriers. So each of these subcarriers occupy different bands, and by measuring the interference from these subcarriers, we can, in a sense, use Wi-Fi to sense BLE. So how do we sense this BLE? We use what traditionally a lot of people call CSI, channel state information. What channel state information is, it provides information to the Wi-Fi receiver of the interference that currently exists in band. So this is your standard Wi-Fi packet. The x-axis is time, the y-axis is the voltage, so we're sampling what's called a baseband of the Wi-Fi signal. Of course, Wi-Fi initially transmits a synchronization sequence. This is what enables OFDM and QPSK to phase lock and time sync to one another. The next thing it transmits after the synchronization is what's considered the channel estimation. This is the CSI information. This is equivalent to, if you're an electrical engineer, you can think of the impulse response, right? This tells you we know what is sent, we can measure the difference of that channel response. Of course, after the channel response, we have the payload. This is ones and zeros. In OFDM, much like your cell phones, your Wi-Fi has this ability to, after you measure the channel response, the interference, you can actually correct for some of the interference levels onto the data bits. So basically, to summarize again, we measure CSI. We use CSI to measure the interference caused by Bluetooth. So in this graph, this is the waterfall display of the spectrum over time. The y-axis, of course, is frequency. The x-axis is time. And you notice the wideband communication, which is this. This is the wideband communication. And that, of course, is the standard Wi-Fi packets being transmitted. This is a BLE packet. It's longer duration. Of course, it doesn't take the whole. It uses a whole lot more less bandwidth, but it lasts longer. So to summarize, we leverage CSI to measure Bluetooth, and this is how we do it. This is a traditional, the last two OSI layer. The traditional link layer, which produces the bits. The bits gets passed to the physical layer. The physical layer takes that bits and transition it to an analog signal that gets up-converted to your right frequency. What we did, or propose to do, is we want to add in our own physical layer. This is the cross-technology communication physical layer. In this, we embed information from Bluetooth and to transmit it to Wi-Fi devices. So this is a standard modulator. It's a variant of the frequency shift key, which we'll talk about later. I'm just going to give you a quick overview of it. This is a standard modulator. We map the bits because BLE is frequency hopping. We do need to map it to a certain amount of frequency. That information gets sent to another Bluetooth receiver. Because Wi-Fi, again, occupies the same band, Wi-Fi sees that interference. Again, what we propose is that we also modify a little bit of we add additional physical layer to the Wi-Fi receiver, and this is our physical layer. And in summary, we do exactly the opposite thing. We extract out the CSI information, and then we also demodulate the embedded Bluetooth signal. So now I'm going to talk about the modulation scheme. So I'm going to go through each one of these. In the example, I'm going to use a variant of FSK. If you want to read our paper, we also did PAM, but you can do a whole whatever modulation you please in our scheme. So if you're not familiar with differential amplitude frequency shift key, what we call DAFSK, basically we carry ones and zeros in terms of frequency. So in other words, we have a oscillator, and we vary the frequency of the oscillator to carry some ones and zeros. So of course, we map each one of these we consider a symbol, and of course, depending on whatever frequency it is, we produce ones and zeros. And this is of course the information we are embedding in a Bluetooth device for Wi-Fi to receive. After the modulation scheme, we of course map this to different frequencies because BLE is frequency hopping. So I'll just talk briefly about the symbol mapper. So it's basically a buffer and a switch. The buffer identifies what power level is being transmitted. The intensity of the color represents the amplitude of the previous slide, the sine wave, basically. And we map this to just different frequency ranges in order. So as signals get mapped, this essentially produces a sine wave, and then, of course, you have multiple slots, multiple frequency ranges. We just map it all over the desired frequency range for the BLE to frequency hop. So now I'm going to just talk briefly about the Wi-Fi receiver. The Wi-Fi receiver is similar. It pretty much very simply reverses whatever modulation and mapping schemes that we produce. So again, this is the original physical layer to the original physical layer to a link layer Wi-Fi receiver. We add in our own physical layer. We extract out the CSI, and then we demodulate. It's pretty much the exact opposite of the Bluetooth transmitter. So if we were to look at this, this is an animation. If we were to look at this, what the Wi-Fi sees, so the y-axis is time, so we're looking at over time, and all of our frequency bands which Wi-Fi occupies, you will see these different power levels of Bluetooth. We unmap it. We produce basically a single array of the intensity of a single array of Bluetooth interference levels, and of course we produce the ones and zeros. It's a fairly standard scheme for demodulating FSK. So again, I just wanted to show you the final summary of our system diagram. So we embed information via power for Bluetooth. We change the power of transmission to Bluetooth, and we receive that information using Wi-Fi. So now I'm going to talk about how we actually perform this experiment. So we developed an RF testbed. This RF testbed has the ability to record, stream continuous, the entire 802.11 or the 40 megahertz ISM band. We downconvert that, we digitize it, and we store it to a RAID. And this is continuous, and that's hence why we need the RAID drives. So you're talking about several gigabytes of data for a second or so. We have the ability to take that same data and upconvert it to basically reproduce the analog waveform, which is just the reverse, and we have the ability to upconvert it to whatever frequency range we desire. So we did a control or a base case. It's a Faraday cage. We removed the interference from our environment, and we have multiple Bluetooth device and Bluetooth and Wi-Fi device in the same bed, and we were able to capture that. We also performed this in line of sight, and it's very similar. We just moved the Bluetooth at different ranges, and we also did it in non-line of sight, which is they were just in two different rooms, and we were able to move the distance between the Wi-Fi and Bluetooth devices at different distances. Again, this is just showing some of the raw data. So we were able to, we did two different type of modulations. We did pulse amplitude, which is similar to the alphabet scheme, which kind of inspired it. So in the pulse amplitude, the PAM modulation, we had 8 different states, and these 8 different states basically transmits ones and zeros. So the 8 states were provided different symbols, which carried ones and zeros from Bluetooth to Wi-Fi. Again, we also did a 4-carrier frequency shift key, and the 4 frequencies provided 4 different states, and we were able to sense that interference from Wi-Fi devices. Again, to compare to the latest freebie communication, because we were able to use these modulation states, and we were able to use CSI with multiple frequency range, we were able to get about 85 times faster than freebie connection technology. Of course, we didn't have anything else to really compare by, so we just compared. We wanted to perform the experiment with different modulation schemes just to verify that our scheme works, and kind of basically to reproduce the variations between PAM modulation and FSK modulation. So of course I'm just picking out a couple of results. If you're more interested in results, you can of course read the paper. So in line of sight, we did at different distances up to 10, 12 meters. It's basically a rolling chair that rolled down the office, and we measured the throughput, the bits per second. We discovered at around 5 meters, the PAM and the FSK, DAFSK was about equivalent. Of course, PAM has, because it had 8 states, it had much higher throughput at close ranges with low interference. But it's not as robust compared to the FSK, which uses a sine wave, which is the standard. This is what your standard telecommunication modulation scheme. FSK enables a far greater distance than PAM. And then we also did non-line sight. Of course, you can see that the PAM had much lower throughput because of the interference, the multipathing that occurs when you're in non-line sight. But again, around 5 meters, we experienced similar throughput. So this just to summarize my slide. So again, we produced an N-way concurrent cross-technology communication scheme by measuring CSI and embedding by using Bluetooth to interfere with Wi-Fi devices through a controlled and modulated scheme. We embedded messages and Bluetooth packets by varying the power level. We sense that power level change using CSI, and then because we used a telecommunication modulation scheme, we were able to significantly increase the bit rate, and because we had much more large amount of bandwidth, we were able to increase the number of frequencies, also frequency states. So, and that summarizes my work. So, are there any questions?
We have time for questions.
Hi, I'm Rahman from Missouri SNT. So I was interested in your modulation technique.
Mm-hmm.
If I'm not wrong, I guess you're using like FIFO buffers, parallel FIFO buffers,
Yes.
and you're storing information there, and you're actually passing it sequentially, not in parallel, right?
Yes, that's correct.
Yeah, so why don't you just,
This?
what's the main purpose of using these FIFO parallel buffers then?
Well, the reason we use this is because Bluetooth, of course, frequency hops. You need for each of the frequency slots, you have to basically schedule schedule a certain amount of packets, right? In one instance, you also have almost like non-ordered arrival times. Also, that's why you have to schedule the packets into a specific time and frequency, and that's why we use multiple buffers.
Could you suggest any other better ways to do it? Or?
Yeah, there's probably other better ways to do it. I mean, we're investigating this too. So one of our current train of thought is with IoT devices, you have all these devices are around you, and then you have a server, and is there a way to basically transmit data, like almost like a software-defined data, where a single piece of data needs to go to a certain device, right? So we're currently thinking that through. Is there different ways to remap the buffer with some sort of like hash table, and enable just basically random data to be sent to a specific device here and there? So.
Okay, so just one more question. Like you are also modifying the hardwares of those like Wi-Fi and Bluetooth device, or
So we don't modify the hardware. We basically in the Bluetooth device, test device, embedded device, we have the ability to set the power levels of each packet that's being transmitted, and that's what we're doing. If you want to go back, we can also talk about the way that we perform the experiment. The way that we perform the experiment is an RF testbed, and in this RF testbed, we have the ability to basically down-convert, basically record signals, but we also have to remember that we have the ability to reproduce the same signals with the same fidelity. So in one instance, in the large-scale experiments, we could, it's almost like Photoshop, right? You can take a packet and you can move it anywhere you want and specify whatever frequency you want and whatever energy level you want. So, and then you also can replay this device, the signal that's recorded, and hear it back to your Bluetooth device or back to your Wi-Fi device for it to modulate. Does that make sense?
yeah, thank you.
Any other questions? Okay, let us.
Oh, there's one more.
Oh, sorry.
Yeah, I actually have a question.
Sure.
You just mentioned that you are able to modulate the power of each packet, right?
Yes.
So you do it in the user space, right? In a computer system, some OS. But how do you verify the power of the packet transmitted over the antenna is actually modified?
Oh, I mean, we have both spectrum analyzers, and we use our RF testbed, which has the ability to record.
But the packet rate is pretty fast, right?
Huh?
Packet rate is pretty fast. You
Yes.
cannot see it
So this,
visually.
yeah. So remember, this is continuous. So we capture every single packet that's being transmitted. This is lossless recording.
Okay, thank you.
That's how we verify each packet.